Welcome to the Deep Dive. Today we're digging into Chapter 11 of the Helicopter Flying Handbook. It's all about helicopter emergencies and hazards, the tricky stuff.
Yeah, the situations pilots train for constantly, hoping they never actually face them.
Exactly. And our mission here is simple. We want to pull out the absolute key insights from this material. We'll unpack the procedures, uncover some maybe surprising facts, and really get you up to speed on what pilots need to know when things go wrong.
Because understanding these potential issues, whether they're mechanical or maybe pilot-induced, it's fundamental. Knowledge is safety.
Absolutely. It's about anticipating, not just reacting. So let's dive right in.
Sounds good. It's a complex world, helicopter flight. Things can change fast.
Okay, so the bedrock emergency procedure, the one everyone knows about, is autorotation.
Right, the power-off descent.
The helicopter's version of gliding, kind of. Engines off, you're coming down. But let's quickly zero in on the why. How does it actually work?
Okay, so the key piece of tech is the freewheeling unit. It basically acts like a one-way clutch. When the engine RPM drops below the rotor RPM, like in an engine failure, this unit automatically disconnects the engine from the main rotor transmission.
So the engine stops driving the blades.
Correct. And the rotor is then free to spin on its own. What keeps it spinning is the air flowing up through the rotor disc as the helicopter descends.
Ah, okay, so the descent itself powers the rotation, like a pinwheel.
Exactly. A very sophisticated, very critical pinwheel effect, yeah. It's driven solely by that upward airflow.
And the main reasons you'd need to do this are obviously engine failure or maybe a failure in the driveline.
Those are the big ones.
Yeah.
But also, interestingly, a complete tail rotor failure often necessitates an autorotation.
Why is that? I thought the tail rotor was for counteracting torque.
It is, in powered flight. But in autorotation, since the engine isn't driving the main rotor, there's almost no torque being produced. So you don't need the tail rotor for anti-torque anymore. It does still provide directional control, but the main reason for it is gone.
Got it. And the source mentions that underlying causes for engine or drive issues can often be things like maintenance problems or fuel issues.
Absolutely. Fuel contamination, running out of fuel. These things happen, and they can lead directly to needing an autorotation. It shows how vital those routine checks are.
Okay, engine quits. What's the very first, most critical action?
Collective down. Immediately. No hesitation.
Full down.
Yes. Lower the collective pitch fully. This instantly reduces the angle of attack on the blades. That reduces lift and, importantly, drag, and initiates the descent.
And you need that descent because?
That's what generates the upward airflow through the rotor disc. That airflow is the only thing keeping the rotor RPM in the safe operating range. If you delay, especially in helicopters with low inertia rotor systems, blades that don't store much energy, the RPM can decay incredibly fast.
And recovering lost RPM is tough.
Very tough. And that may be impossible if it drops too low. So immediate collective down is paramount.
Okay, descending keeps the blade spinning. How do you control how fast you're coming down?
Primarily with airspeed, which you control with the cyclic stick. And you manage the rotor RPM itself using small adjustments of the collective. There's usually an optimal airspeed range. The handbook suggests around 50-60 knots for many types. That gives you the minimum rate of descent.
Slower or faster means coming down quicker.
Generally, yes, which means you'll have less time and potentially a harder landing.
Right. And speaking of landing, where does the energy to cushion that touchdown actually come from? The engine's off.
It comes entirely from the kinetic energy stored in those spinning rotor blades. That mass spinning around holds energy.
So maintaining that rotor RPM during the descent isn't just about keeping control, it's storing energy for the landing.
Precisely. That's your energy reserve. The higher your descent rate when you reach the ground, the more of that stored energy you'll need to arrest the descent smoothly.
So you're constantly managing that RPM, keeping into the green range.
Exactly. Typically in what's called the low green area on the gauge for autorotation, if the RPM starts getting too high, you raise the collective just a tiny bit.
Increasing pitch adds drag, slows the blades.
Right. And if RPM starts to decay, you lower the collective slightly to reduce drag and let the airflow speed them back up.
But not big jerky movements.
No, absolutely not. Smooth, small inputs. The source warns against chasing the RPM with large corrections.
And getting everything right, collective down, cyclic adjusted, pedals for trim, all at the same instant the engine quits. Especially in those low inertia helicopters, that sounds incredibly demanding.
It is. The material emphasizes simultaneous inputs. Down collective, aft cyclic, Aft cyclic helps prevent the nose from dropping excessively and maintains airflow and aligning with the relative wind using pedals. All at once. It even notes a pilot tendency to sometimes lean forward in surprise, which can delay these critical inputs.
And compared to an airplane, a helicopter auto-rotating doesn't cover much ground, does it? The glide ratio is poor.
Much, much lower. That's a key difference. You're coming down much more steeply than a fixed-wing aircraft gliding. So understanding how your airspeed affects both your rate of descent and your forward glide distance is vital for picking a landing spot you can actually reach.
Practice at different airspeeds is key then, to know what gives max distance versus minimum sink.
Essential.
Okay, so the simplest auto-rotation is straight in, no turns.
Right, just coming straight down from altitude to a landing spot ahead. Wind is a huge factor here.
How so?
A headwind doesn't change your rate of descent much for a given airspeed, but it dramatically reduces your ground speed. This makes your glide path over the ground much steeper.
Which is actually good for landing, right? Slower touchdown.
Exactly. A good headwind is your best friend in an auto-rotation landing. It minimizes ground run and reduces the energy you need to dissipate in the flare.
Oh, let's talk about the flare. That maneuver right at the end to slow down.
Okay, at a specific altitude recommended by the manufacturer, it varies. You apply aft cyclic. You pull back on the stick. This pitches the nose up, using your forward airspeed to generate a temporary increase in lift, which slows both your forward speed and your rate of descent. You use the pedals to keep pointing straight.
Goal is to slow down to like a running speed.
Yeah, something manageable. The timing and smoothness are critical. Pull back too hard or too fast, you might balloon upwards briefly. Too slow, and you won't arrest the descent rate enough.
And after the main flare, you have to adjust again.
Yes, you need to push the cyclic forward slightly to get the helicopter into a level or slightly nose-up attitude before touchdown. If you land flare attitude, tail low, you'll almost certainly strike the tail rotor.
That tail strike danger zone below 10 feet sounds serious.
Very serious. You must achieve the correct landing attitude.
Then the final bit, the touchdown itself.
Right, sometimes called position 5. You're descending vertically. Just before touchdown, maybe a few feet up, you smoothly raise the collective pitch.
Ah, now you use that stored energy in the blades.
Exactly. Raising the collective increases the angle of attack on the blades, creating lift that cushions the landing, slows that final descent rate. But doing so rapidly uses up your rotor RPM, your energy.
And you mentioned needing opposite pedal?
Correct. When you pull collective in an auto-rotation, transmission friction and other factors create a yaw that needs opposite pedal input compared to powered flight to keep the nose straight. The aim is a gentle touchdown in a level attitude. Don't try to hold it off the ground until all energy is gone. That leads to a stall, a drop, and a very hard landing. Likely damage.
Looking at the common errors for straight-in autos, not entering immediately seems like the biggest one. Delay is fatal to RPM.
Absolutely critical. Others include messing up the anti-torque, incorrect pitch attitude, not managing RPM, pulling collective too soon or too high, failing to level off properly, drifting sideways.
And crucially, in practice, not going around if things aren't right.
Yes. If the approach isn't stabilized by the minimum decision height, executing a power recovery or go-around is the safe call.
Which brings us nicely to auto-rotations with turns. Sometimes you need a maneuver to reach a safe spot or land into the wind.
Very common. Typically 90 or 180-degree turns are practiced. The key is to make the turns early in the descent while you still have altitude.
How does a 180-degree turn work in practice?
You usually establish a downwind leg flying parallel to your intended landing path, offset slightly to account for wind drift. Abeam your chosen touchdown spot, you initiate the auto-rotation, reduce collective power, split the needles, apply appropriate anti-torque and cyclic for attitude and entry airspeed. Then you smoothly roll into the turn, typically aiming for a bank angle between 30 and maybe 60 degrees.
And you're juggling airspeed, RPM, and trim throughout the turn.
Constantly. Maintaining target airspeed, keeping RPM in the green with small collective adjustments, and staying coordinated, keeping that trim ball centered. Bank angle itself affects RPM due to G-loading, so you manage that. The handbook also cautions that the airspeed indicator can lag or be unreliable in a turn, so you don't want to chase the needle with aggressive pitch changes. Rely more on attitude and known power pitch settings.
And you check your position relative to the landing zone partway through.
Yes, usually around the 90-degree point of a 180 turn. Are you on track? Too close, too far. You adjust your bank angle, less bank to widen the turn, more bank to tighten it up, but not exceeding limits like 60 degrees. The aim is to roll out of the turn, aligned with your landing spot, with any necessary crosswind correction applied, ideally by about 200 feet above the ground.
And there are strict rules for practice autos about whether you can continue from that point.
Absolutely. By that 200-foot point, the approach must be stabilized. That means aligned, into wind preferably, RPM within limits, proper airspeed and attitude, and the aircraft fully under control. If any of those aren't met, the procedure is to abort the autorotation and execute a power recovery and go around immediately. Trying to salvage a bad approach lowdown is much riskier than going around.
Makes perfect sense. Trying to force it just eats up your safety margin.
Exactly. Things like delaying the turn means you arrive on the final approach course at a lower altitude. Flying uncoordinated with the trim ball off-center increases your sink rate, both reduce your options and margin for error.
And the scan during the turn is split between outside references, attitude, turn rate, and inside instruments, RPM, trim ball.
Correct. RPM is always primary. It's your lifeline. G-forces in the turn and flare tend to build RPM, so you manage that with collective.
And that final collective pull is timed just right to use the stored energy.
Yes, raising collective increases angle of attack, gives you that cushion, but rapidly decays RPM. Timing the flare and that final collective application is the art and science of it. During the flare itself, your scan is almost entirely outside, judging height, closure rate, attitude with quick glances inside at airspeed and RPM.
And factors like wind, density, altitude, gross weight, they all change how much flare you need and how the helicopter responds.
Significantly. High-density altitude, for example, means you'll have a higher descent rate, less tendency for RPM to build, maybe a slower initial engine response if you needed power, requiring you to start the flare a bit higher and perhaps be more aggressive.
The list of common errors for turning autos basically adds turn-related mistakes onto the straight-in ones, right?
Pretty much. Improper entry, bad transitions, uncoordinated flight, failing to correct for drift, messing up the flare timing or magnitude, not maintaining RPM. The turn adds another layer of complexity.
Okay, we mentioned power recovery. That's how you typically end a practice auto rotation before actually touching down.
Right. It allows you to practice the whole sequence safely, ending in a hover or a go-around.
How's that executed?
As you approach the ground, say 3 to 15 feet, depending on the type, you start leveling the helicopter with forward cyclic, aiming for a slightly nose-up attitude. Then, just before you reach that level attitude, you simultaneously and smoothly raise the collective and roll the throttle back up towards flight power.
Coordinating collective and throttle is the key.
Absolutely critical. You're trying to rejoin the needles, get the engine RPM back up to match the rotor RPM smoothly. Too much throttle, too fast risks overspeeding the engine. Too little throttle or too slow, and the rotor RPM will decay before the engine catches up. You need enough collective to arrest the descent, but smoothly enough to allow the engine time to respond. And you need to coordinate pedals to counteract the engine torque coming back in.
Does it matter where the throttle control is?
Yes, significantly. On many trainers, the throttle is a twist grip on the collective. You roll it from idle back to flight power as you raise collective. On others, the throttle might be separate. For practice power recoveries, you might leave it set near the flight position, ready for quick reapplication. But for a full touchdown auto, you'd move it to idle. You have to know your specific aircraft.
And engine type matters too. Piston versus turbine.
Definitely. Turbines generally have a bit more lag in spooling up compared to a responsive piston engine. Turbocharged pistons can also have some lag. The handbook suggests if you have a slower responding engine, you might need to initiate the power application a bit higher, maybe around 100 feet AGL during the practice auto, to ensure the engine is delivering power by the time you reach the flare height.
Wow. That sounds like a very high workload maneuver in those last few seconds.
Extremely. Transitioning from unpowered descent, flaring, leveling, coordinating throttle and collective, managing pedals for torque, all happening very fast, very close to the ground.
And the common errors reflect that complexity, starting too late. Bad coordination, not leveling properly.
Exactly. And again, the biggest potential error is failing to recognize it's not working out and not executing a timely go-around.
Okay, what if the engine fails while you're just hovering, say, a few feet off the ground?
That's practiced as a hovering autorotation. It simulates an engine stoppage or other emergency right there in the hover.
How does that differ from a forward flight auto entry?
You establish normal hover, maybe 2-3 feet up into the wind, max RPM. Then you firmly roll the throttle to idle. This simulates the failure, disengages the engine via the freewheeling unit, and eliminates the main rotor torque.
So you need right pedal then, typically.
Yes, you apply the appropriate anti-torque pedal to stop yaw, usually some right pedal in a counterclockwise system to counteract aerodynamic forces and transmission friction. You also need a touch of right cyclic to counteract the loss of sideways tail rotor thrust. But here's a key difference. You do not adjust the collective initially. You just hold it steady, maintain a level attitude with cyclic, and let the helicopter settle vertically.
And avoiding any sideways drift is crucial.
Absolutely critical. Any sideways movement while touching down can lead to dynamic rollover, which we'll get to. You want a purely vertical descent.
Does it settle fast?
Depends on the rotor inertia. Low inertia systems settle almost immediately. High inertia systems have a bit more float. As you get very close, maybe a foot off the ground, you apply upward collective smoothly while keeping the throttle at idle. This uses the last bit of rotor energy to cushion the landing, often requires full collective right at touchdown.
And that collective timing is critical here too.
Maybe even more so because you have less time and energy than in a forward flight auto. Pull too soon, you run out of RPM before touchdown. Too late, you hit hard. And never try to hold it off the ground with collective. The blades will stall, lift disappears, and you'll drop hard, likely causing damage.
Common errors. Not enough anti-torque, allowing drift, messing up the collective pull.
Those are the main ones, plus maybe not rolling throttle fully off in practice or starting from an unsafe altitude.
Okay, that covers engine failures pretty thoroughly. But there are other major hazards that aren't necessarily mechanical failures, right? Aerodynamic issues.
Absolutely. The way air behaves around the helicopter can create some very dangerous situations. One of the trickiest is vortex ring state, also known as settling with power.
Settling with power. That sounds wrong.
It feels wrong, too. The key is you're descending vertically or nearly vertically at a significant rate, at least 300 feet per minute, while applying considerable engine power, say 20 to 100%. And despite that power, you have little or no climb performance. You're settling.
Why? What's happening with the air?
You're essentially descending into your own downwash. Instead of clean air flowing down through the rotor disc, the air starts recirculating. The vortices shed from the blade tips get much larger, and air actually starts flowing up through the inner part of the rotor disc. This creates a secondary vortex system. All that engine power is just wasted churning this turbulent air. It's like being caught in an aerodynamic donut of disturbed air.
And once it fully develops, it's unstable.
Very. Uncommanded pitch and roll oscillations, the collective becomes largely ineffective, and descent rates can skyrocket, potentially thousands of feet per minute.
What conditions lead to this? Hovering out of ground effect without good altitude control? Steep approaches with a tailwind?
Exactly. Any situation combining a vertical descent rate over 300 FPM, low forward airspeed, below effective translational lift, and significant power application, 100%, quick stops, recovering from an autorotation near the ground. These can also induce it.
And the instinctive reaction pulling more collective to stop the descent actually makes it worse.
Initially, yes, that's a critical point. More collective increases the blade pitch, which stalls more of the blade area within that recirculating flow, worsening the vortex and increasing the sink rate. Cyclic control might also feel mushy.
So how do you get out of it?
The traditional recovery is to fly out of the vortex. Either increase forward airspeed by pushing forward on the cyclic and/or reduce collective slightly. Get forward speed, fly out of the disturbed air. The material also mentions the Vouchard recovery technique using lateral cyclic to side-slip out of the downwash column while simultaneously increasing power and coordinating anti-torque pedal. It focuses on exiting the descent rather than just the vortex. But the absolute key is early recognition. Feel that mushiness, the unexpected sink rate, maybe some vibrations, recover immediately. Forward cyclic to gain speed, maybe a slight collective reduction, fly through translational lift.
Got it. Now, another major aerodynamic limit, especially at high speeds, retreating blade stall.
Right. This is all about the difference in airspeed over the advancing blade, moving into the relative wind, versus the retreating blade, moving away from it. The advancing blade sees higher airspeed, the retreating blade sees lower airspeed. To keep lift equal across the rotor disc, the blades flap automatically, advancing blade flaps up, reducing its angle of attack. Retreating blade flaps down, increasing its angle of attack.
Okay.
At high forward speeds, the retreating blade is dealing with very low relative airspeed and a very high angle of attack due to that flapping down. Eventually, that angle of attack becomes too great, and the retreating blade stalls. It loses lift.
And this is what fundamentally limits a helicopter's top speed. It's never exceed speed or VNE.
Exactly. And VNE actually decreases as you go higher in altitude. In thinner air, you need higher blade pitch angles overall to produce lift, so the retreating blade hits its critical stall angle at a lower forward airspeed.
What does it feel like if it starts to happen?
Typically a low-frequency vibration, maybe felt in the airframe or controls. The nose might pitch up, and you'll often get a roll towards the stalling side, the retreating blade side. Left roll in a counterclockwise rotor.
And conditions like being heavy, having low rotor RPM, high-density altitude, hitting turbulence, or making steep, abrupt turns at high speed make it more likely.
Yes, anything that increases the load on the rotor system or requires higher blade angles pushes you closer to that stall limit.
Recovery is often counterintuitive here, too. The source says reduce collective first.
That's usually the most effective initial action. Reducing collective lowers the angle of attack across the entire rotor disc, helping the retreating blade regain lift. Applying aft cyclic, like pulling back, actually worsens it because that increases blade angles like a flare. Forward cyclic doesn't directly address the stall either. You also need to address the cause. If you're in a steep turn, roll wings level. If your RPM was low, increase it.
Okay, shifting gears to mechanical issues, but ones that happen on the ground. Ground resonance sounds nasty.
It is. It's a specific, potentially very destructive vibration that only affects helicopters with articulating rotor systems, usually 3 or more blades with flapping and drag hinges while they are on the ground. It's a mechanical issue where an imbalance in the rotor system excites the natural resonant frequency of the airframe.
How does the rotor get unbalanced?
Usually from a hard landing or hitting a bump while taxiing, especially with wheeled gear. The shock can momentarily knock the blades out of their normal, evenly spaced positions around the rotor head. Maybe one blade lags or leads slightly on its drag hinge. This creates an imbalance. As the rotor spins at certain RPMs, this imbalance can match the airframe's natural frequency. If the engine is supplying power, it feeds energy into this vibration, amplifying it incredibly quickly. It can literally shake the helicopter apart in seconds.
So helicopters with rigid or semi-rigid rotors don't get this?
Correct, because they lack the drag hinges that allow that lead-lag motion and imbalance to develop. Skid gear is also less prone than wheels because the struts of skids tend to dampen shocks better and have different resonant frequencies.
If it starts, what's the immediate action?
It depends critically on the rotor RPM. If RPM is low, in the developing range, you immediately close the throttle and lower the collective fully. Get the RPM down below the resonant range quickly. If the RPM is already in the normal operating range, the correct procedure is to lift the helicopter into a hover. Getting airborne allows the aerodynamic and centrifugal forces to recenter and rephase the blades, eliminating the imbalance. Then you can make a normal, gentle landing. But don't touch down hard again until you're sure it's stopped.
Another ground-based hazard, dynamic rollover.
Right. This is a lateral rolling tendency that happens when the helicopter starts to pivot around one skid or wheel that's stuck or acting as a pivot point on the ground. As the helicopter rolls, it reaches a critical bank angle. Beyond this angle, the main rotor thrust, which is trying to lift the helicopter, actually starts contributing to the roll, and cyclic control alone isn't powerful enough to stop it. Recovery becomes impossible.
So you need 3 things. Something causing a roll, a pivot point on the ground, and enough rotor thrust to lift the weight.
Those are the ingredients, exactly.
What causes it? Forgetting to remove a tie-down, hitting an obstacle with the gear, bad technique on slopes.
All of the above. Anything that fixes one part of the gear to the ground while a rolling moment is applied and you have lift being generated.
And you can't just stop it with cyclic control.
Not once it passes that critical angle. The crucial recovery action, the most effective one, is to quickly reduce collective pitch. Lowering the collective reduces the main rotor thrust, taking away the force that's driving the rollover.
The source highlights conditions that make it worse for counterclockwise rotors, like having the right skid down.
Yes, because the natural translating tendency, drift to the right, adds to the rolling moment if the right skid is the pivot. Crosswinds from the left, a right CG shift, left pedal inputs, they all increase the risk on that side.
And it can happen even on level ground during a normal takeoff if one skid hangs up briefly.
Absolutely. That's why smooth collective application and minimal cyclic inputs are key near the ground. If you feel a roll developing, say, beyond 5 to 8 degrees, and full opposite cyclic isn't stopping it, reduce collective immediately.
Slope operations seem particularly tricky.
They require specific techniques for this reason. Landing, you touch the upslope gear first, then gently lower the downslope side with collective and cyclic. Taking off, you level the disc, then lift vertically. If you get excessive roll towards the upslope during landing or lift the upslope skid first during takeoff, you're setting up for dynamic rollover. The recovery is always to reduce collective, relevel, and try again.
So, again, collective is the primary control to stop the roll.
By far the most effective.
Yeah.
A quick, smooth reduction significantly reduces the rolling force. Dumping it too fast could cause issues like mast bumping, but a controlled reduction is key.
The precautions mentioned awareness of wind, two-step liftoff, obstacle clearance, avoiding cyclic limits, careful slope technique, all aim to prevent those conditions from arising.
Exactly. It's all about managing those three factors: pivot point, rolling moment, and thrust.
You mentioned mast bumping when talking about dumping collective. That also comes up with low-G conditions, right?
Yes, and it's a very serious concern, especially for helicopters with two-bladed Kettering rotor systems. Low G is that weightless feeling, like going over the top of a roller coaster. Helicopters need positive G loading for controls to work effectively. The controls tilt the rotor disc, and under positive G, the thrust vector pulls the fuselage along. In low G, that connection becomes weak. Control authority is greatly reduced.
And why is it worse for two-bladed systems?
Multi-bladed systems often have flapping hinges offset from the hub or rigid hubs that provide some direct control moment. But a two-bladed teetering system relies almost entirely on tilting the thrust vector relative to the helicopter's center of gravity. In low G, with reduced thrust, the fuselage attitude becomes much harder to control.
And the dangerous situation arises from an abrupt forward push on the cyclic, a pushover, especially at higher speeds.
That's the classic scenario. Pushing the nose over sharply induces low G. The pilot might lose effective pitch control of the fuselage. Then, aerodynamic forces, or tail rotor thrust, can cause an uncommanded roll, often right for counterclockwise rotors. The pilot instinctively applies opposite cyclic to correct the roll, tilting the rotor disc. But because of the low G condition, the fuselage doesn't follow the disc attitude. The angle between the tilted disc and the largely unresponsive fuselage becomes excessive. The rotor hub hits the mast that's mast bumping.
Severe turbulence can also cause this.
Yes, strong downdrafts at high airspeed can momentarily unload the rotor, creating a low G state.
And the consequences are bad.
Catastrophic. The forces involved can sever the mast or cause blade strikes on the airframe. It happens very quickly.
So the key takeaways are: avoid abrupt forward cyclic, especially in two-bladed Heelys. Recognize that weightless feeling as the onset of low G. Recognize an uncommanded roll as a potential loss of control. And crucially, if it happens, the recovery is gentle aft cyclic first to reload the rotor and restore positive G before trying to correct the roll.
That sequence is vital. Restore G, then correct attitude. It's counterintuitive to pull back when you're rolling, but necessary in this specific situation. Simulators are great for practicing recognition and recovery.
Okay. Another critical parameter: low rotor RPM.
Absolutely fundamental. A helicopter simply cannot fly if the rotor RPM drops below a minimum safe speed. The blades will stall.
How is this different from the retreating blade stall we talked about earlier?
Retreating blade stall is localized to the retreating blade tip at high forward speed, causing vibration and control issues but still producing lift. Low rotor RPM stall affects the entire rotor disc, can happen at any airspeed, and results in a total loss of lift and a rapid descent.
So more like an airplane wing stalling completely.
Conceptually, yes. In both cases, the angle of attack gets too high for the given speed. Airspeed for a wing, rotational speed for a rotor blade. Airflow separates, lift is lost, drag increases dramatically. However, a rotor stall is particularly nasty. Because of the upward flow of air in a descent, the angle of attack can get so high that even lowering the collective fully might not be enough to restore attached flow. Plus, it's not symmetrical. The retreating blade stalls first, causing the whole rotor disc to tilt sharply backwards, rotor blowback. At the same time, the descent causes airflow to hit the tail boom and stabilizers, pitching the nose down. If the pilot instinctively pulls aft cyclic, it worsens the blowback and the blades can strike the tail boom.
And you lose tail rotor effectiveness too, since its speed is tied to the main rotor.
Correct. Complete loss of directional control as well.
The source is blunt. Rotor stalls are generally not recoverable.
At low altitude, impact is basically guaranteed. Higher up, the chances are extremely slim. This underscores why early recognition and immediate correct recovery from decaying RPM is absolutely imperative. It must be a conditioned reflex.
What causes RPM to decay that badly?
Can happen in an autorotation if you're too slow lowering the collective initially, or if you pull too much collective too high up near the end. But the source says the more common cause is actually a power-on situation, over-pitching.
Meaning pulling too much collective.
Exactly, demanding more power from the engine than it can possibly deliver at that altitude and weight. This is a huge risk at high-density altitudes when heavily loaded, if the engine governor fails, or if the pilot mishandles the throttle. You pull collective, the blades demand more power, the engine can't provide it, so the RPM drops.
And it becomes a vicious cycle.
Yes. Lower RPM means less power available from the engine, which makes RPM drop faster. If the helicopter starts settling and the pilot pulls more collective trying to stop it, it accelerates the decay right into a stall.
Recognizing it quickly is key. Besides the tachometer, what are the cues?
Yeah.
Yawing, noise change.
Yes, unexpected yaw due to changing torque, decrease in engine or rotor noise, possibly vibrations, and importantly, the low RPM warning horn or light.
And the recovery action is simultaneous and automatic.
Absolutely, simultaneously. Lower collective, increase throttle, if power is available, and apply aft cyclic as needed to maintain attitude. At higher speeds, aft cyclic also helps unload the disc and allows RPM to recover faster. Do this first, then figure out why it happened.
Okay, let's talk about specific system failures. Anti-torque system failure sounds like a big one.
Huge. Losing yaw control is critical. Two main types. First is a complete loss of tail rotor thrust drive failure, gearbox, maybe the blades depart. Without anti-torque, the fuselage immediately starts spinning in the direction of main rotor torque, usually right for U.S. helicopters. How fast it spins depends on how much power you had on and your airspeed.
High power, low speed equals fast spin.
Very rapid. Low power, high speed, a slower spin, because the airflow over the fuselage and vertical fin provides some stabilizing effect.
Recovery from complete failure.
Reduce main rotor torque immediately. That means entering an autorotation. Lower collective, roll throttle to idle. If in a hover, it's a hovering auto. If you have enough forward speed, you might maintain some directional control using the vertical fin to glide towards a landing spot. Slight cyclic opposite the spin might help, but adds drag. Airspeed is key. Throttle location can be a factor here too. If you need forward speed for fin effectiveness, but the throttle isn't on the collective, managing everything gets trickier. Low altitude failure gives you very little time.
What's the second type of failure?
A mechanical control failure. The pedals might jam or a control rod breaks. The tail rotor is still producing thrust, but you can't change its pitch, it's stuck. In this case, autorotation is generally not required because you still have anti-torque, just not variable anti-torque.
And the landing technique depends on where the pedal is stuck, left versus right.
Exactly. If it's stuck left, high power setting needed for level flight, reducing power will cause a left yaw. You'd typically fly a steeper approach, keeping power on until just before touchdown. Then, as you flare and need less power, you increase collective smoothly to use the changing torque to align the nose and cushion. If it's stuck neutral or right, low power setting, you'll get right yaw as you add power. So you fly a shallower approach at minimum controllable airspeed. The landing is often a run-on landing, where you reduce throttle as you touch down, coordinating with collective to maintain heading and cushion.
Trying a go-around with a stuck pedal sounds risky if you apply power too quickly below translational lift speeds.
Very risky. Could induce a rapid spin. Careful power application is key.
Okay, what about loss of tail rotor effectiveness, LTE? The source emphasizes this is not a mechanical failure.
Crucial distinction. LTE is purely aerodynamic. It's an uncommanded, often rapid yaw, again, usually to the right, because the tail rotor temporarily isn't producing enough thrust for the pilot's tuttle input, even though it's working mechanically fine.
Why does that happen?
The tail rotor needs relatively clean, stable airflow. If that airflow is disrupted by main rotor downwash, main blade tip vortices, turbulence, or specific wind directions relative to the helicopter, the tail rotor's efficiency drops. The same tuttle input produces less thrust, leading to an imbalance in yaw. Factors like high power settings, more downwash, slow airspeed, below effective translational lift where the tail rotor works hardest, and certain wind directions are prime contributors.
Which wind directions are worst?
The handbook highlights several. Winds from the left front quadrant around 10 o'clock, 15 degrees, can blow main rotor vortices directly into the tail rotor. Tailwinds, roughly 120 to 140 degrees, can cause a weathercock stability issue where the helicopter wants to swap ends. Left crosswinds around 210, 330 degrees can put the tail rotor into its own vortex ring state, causing thrust fluctuations.
And combinations make it worse.
Definitely.
High-risk activities, low and slow operations.
Yes. Patrol, observation, ENG, power line work, anything involving low airspeed flight, OGE hovering and maneuvering near obstacles or in unpredictable winds.
So the key, awareness, recognize the conditions where LTE is likely, and react instantly if an uncommanded yaw starts.
Understanding the why helps you avoid those conditions. If it does happen, the recovery is standard. Simultaneously apply full opposite left pedal, push forward cyclic to gain airspeed, and fly out of the disturbed air. Reduce collective if altitude permits. That helps reduce torque demand, but increases descent rate. It's a judgment call based on height.
And if it becomes uncontrollable near the ground, auto-rotation.
Yes, that's the last resort. Full left pedal until the rotation stops, then execute the auto. The source makes a really important point here. Pilots have mistaken LTE for a tail rotor failure and auto-rotated unnecessarily. Knowing about LTE might allow you to fly away instead.
What if the main drive shaft or the clutch between the engine and transmission fails?
That has the same effect as an engine failure regarding the main rotor power is lost. You must auto-rotate immediately. One key difference is the engine, now unloaded, will likely overspeed, so you need to close the throttle instantly. Also, depending on the design, the tail rotor might still be driven by the engine, so a tail rotor overspeed is also possible. Close throttle, auto-rotate. Know your system. Generally, if you suspect a drivetrain issue, check your RPMs. If main rotor RPM is decaying despite engine power, it's likely a drive failure or auto-rotate. If RPMs are normal, it might be an instrument issue.
Hydraulic failure. That means heavy controls.
Extremely heavy. Most helicopters rely on hydraulics to move the flight controls. Warning signs might be grinding noises, stiff controls, or feedback forces you don't normally feel. First actions are usually to reduce airspeed, less force needed. Check the hydraulic switch breaker. If it doesn't come back, a shallow approach to a running or roll-on landing is usually recommended. It requires much less control effort than trying to hover precisely. You'd also typically disable the hydraulic switch to prevent it restoring unexpectedly.
Some have backups.
Yes, dual systems or accumulators providing temporary pressure.
Governor or fuel control failure. That's the system managing engine RPM, right?
Correct. It automatically adjusts fuel flow to keep rotor RPM constant as you move the collective. If it fails, the pilot has to manage engine RPM manually with the throttle. If it fails high side, the engine overspeeds. If you can't control it with throttle, you might have to shut down and auto-rotate. If it fails low side, the engine doesn't produce enough power. You'll have to lower collective to maintain RPM. A running landing might be possible if you have enough power. Otherwise, again, auto-rotation.
Abnormal vibration. Helicopters vibrate normally, but how do you tell what's bad?
Experience, knowing your specific aircraft's baseline. Abnormal vibrations are warnings. They're often categorized by frequency. Low frequency feels like a beat, 100, 500 cycles min, is usually the main rotor out of track or balance. Medium frequency, buzzing, 1,000, 2,000 CPM, could be accessories, fans, parts of the drivetrain. High frequency, 2,100 CPM, is often the tail rotor, or could be engine-related, piston engine misfire, turbine issues.
Modern tools help diagnose.
Yes, vibration analysis equipment, track and balance kits, HUMS health and usage monitoring systems can pinpoint the frequency, amplitude, and likely source, guiding maintenance.
Okay, shifting from mechanicals to other flight challenges. Getting lost.
A classic aviation problem. Disorientation, unfamiliar area, bad visibility, high workload. The absolute priority if you realize you're lost, fly the aircraft first, maintain control, then work the problem.
And a big hazard when lost and potentially low is wires.
Invisible killers. Always look for the supporting structures, poles, towers, especially near roads, rivers, buildings.
Basic procedure is look for landmarks on your chart. Rivers, towns.
Yeah, try to match ground features to the map. See a town name on a water tower? Land safely nearby and ask.
If no landmarks are obvious, the advice is to climb.
Generally, yes. Climbing improves visibility over a wider area, increases radio and navigation signal range, and gives you better terrain clearance. It's the first C in the 4 Cs. Climb, communicate, confess, comply.
Let's run through those quickly.
Climb to a safe altitude. Communicate, try flight service, 122.2, ATC frequencies from your chart, or emergency 121.5 and squawk 7700. Confess, tell ATC you are lost and need help. Comply, follow their instructions. They have radar and resources.
Better to prevent it, though. Flight following. Checkpoints.
Absolutely. Situational awareness is key. Know where you are relative to planned checkpoints. Use VORs if equipped. Get flight following from ATC.
Getting lost and being low on fuel is a nightmare scenario.
Doubly dangerous. The helicopter's advantage is landing almost anywhere. The smart move is a precautionary landing before fuel is critical. Find a field near a road. Getting fuel brought to you is much better than an accident.
The other major non-mechanical threat, VFR flight into IMC instrument meteorological conditions.
Probably the single biggest weather-related killer in general aviation, including helicopters. VFR pilots rely on seeing the ground and horizon. Fly into cloud or fog, you lose those references instantly. Without instrument training and currency, spatial disorientation is almost immediate, often leading to loss of control. Many helicopters aren't IFR certified. Pilots lack real IMC time, and the reliance on visual cues is strong.
Avoidance is the only real answer.
Absolutely. Prevention is key. Have conservative personal weather minimums stricter than the regulations. Get a thorough weather briefing. Recognize deteriorating conditions early.
What's the decision point? When do you have to turn back or land?
When conditions approach or go below your personal minimums, signs you're getting close. Having to descend lower and lower to stay clear of clouds, needing to slow down significantly because visibility is dropping. If the ceiling or V's is trending down, make the decision before you're in the soup.
If you are instrument-rated, current, proficient, and in an IFR-equipped helicopter, what's the procedure if you blunder into IMC?
First, ensure you're at a safe altitude check charts for MSA, MOCA, etc. Climb if necessary. Stabilize the aircraft on instruments. Then declare an emergency with ATC. Remember, aviate, navigate, communicate, fly the helicopter first.
And if you're not instrument-rated or the helicopter isn't equipped?
Staying VMC is paramount. The deadly trap is pushing lower, trying to follow roads or rivers. You fixate downwards, miss obstacles ahead like towers or rising terrain, then react too late or become disoriented, maneuvering. Extremely dangerous.
Night flight makes it even harder.
Much harder to see deteriorating weather. Needs even higher minimums, more vigilance. Always have pre-planned landing options along your route.
So basic VMC guidelines. Turn around early. Don't push on if you can't see terrain clearly. Delay or cancel if weather is iffy. Trust your gut.
And always have an out, a safe place to land if needed.
The source gives 5 steps if you do inadvertently enter IMC and have basic instrument skills displays.
Right. 1. Level wings, attitude indicator. 2. Set climb attitude airspeed. 3. Verify climb established. 4. Set climb power. 5. Maintain heading, obstacle-free, trim.
And avoid an immediate 180 turn.
Yes, that's a recipe for disorientation. Stabilize first, then make a controlled standard rate turn if needed, using instruments.
Every IMC situation is different, of course.
Terrain, obstacles, icing, performance, ATC, many factors, but the overarching message is planning and prevention are far better than trying to recover. An instrument rating is a lifesaver.
Finally, the handbook touches on survival gear.
Important consideration, especially for remote operations. It's required in places like Canada and Alaska, and highly recommended over desolate areas. What you carry depends on the environment, weather, duration, but always limited by the helicopter's space and weight capacity.
It lists quite a few items.
Yeah, things like food, water purification, shelter tents, fire starting matches, signaling, mirror, pyrotechnics, tools, knife, axe, saw, navigation compass, first aid, insect protection, flashlight, portable ELT.
And specific items for winter like snowshoes, sleeping bags.
Right. Tailoring the kit to the expected conditions is key. Just another layer of risk management.
Okay, so that wraps up our deep dive into Chapter 11. We've covered a lot from the fundamentals of autorotation and its variations
to those unique aerodynamic hazards like vortex ring state, retreating blade stall, ground resonance, dynamic rollover.
The dangers of system failures like hydraulics or tail rotor issues, low G, low RPM.
And handling being lost or inadvertently entering bad weather, plus the need for survival gear.
It really highlights the unique challenges of helicopter flight. Emergencies are a reality, but knowledge, anticipation, practice, those are the pilot's best tools.
Absolutely. Understanding how things can go wrong is the first step to preventing them or managing them effectively if they do.
Which leads us to our final thought for you, the listener. When you think about these incredibly specific, high-stakes challenges faced by helicopter pilots, managing complex machines, dealing with rapid onset failures, operating right at the edge, how does that illuminate broader principles? What can you take away about preparing for the unexpected, about understanding complex systems, about critical decision-making under pressure, even if your own field is completely different? What does this deep dive into helicopter emergencies tell you about managing risk and building resilience in any complex endeavor?
It's a fascinating question. That need for deep system knowledge, for practiced responses, for clear thinking when things unravel. Those principles seem pretty universal, don't they?
They really do. Well, thank you for joining us on this deep dive. We hope this look inside the demanding world of helicopter emergency procedures was insightful and maybe gives you a new perspective on managing complexity and risk wherever you encounter it.